Hello everyone, thank you for joining this season. Today we are demonstrating the TDM's application in a city-scale project, so the Red Sea project. My name is Haishan Wang. I come from Cyber 3, a subsidiary company of Power China Group. Currently, I'm the engineering director of Cyber 3, and due to the importance of the project, I'm also the engineering manager of this project. I feel very honored to be invited by ETAP to participate in this event, and I hope that my brief introduction to the application of TDMS system in this project can bring something new and valuable to everyone from the perspective of EPC. Now, let's start the presentation. Today, my presentation includes three parts. Number one, introduction of Cyber 3 and Red Sea. Number two, the introduction of ETAP's TDMS used in the Red Sea project. Number three, some findings or specific cases in this project. Now let's move to the first part. Introduction of Cyber 3 and the Red Sea project. Cyber 3 was founded in 1985. It's an 8-level subsidiary of Power China Group. In the year 2000, our first overseas project landed in Nigeria, starting exploration of overseas projects. Our company actively responds to the Chinese national One Belt, One Road policy. More than 6 construction projects have been carried out in more than 20 countries. For example, Saudi Arabia, the UAE, Iraq, Oman, Jordan, Egypt, Uzbekistan, Pakistan, India, Indonesia, Nigeria, South Africa, and other national markets. The contract value has exceeded more than 26 billion US dollars. The performance of our company demonstrates the strength of China and the wisdom of China to the world with concrete actions. Now, let me introduce the Red Sea project. This project is the first large-scale project in Saudi under the plan Saudi Vision 2030. According to this plan, in order to reduce the country's dependence on oil economy and diversify its economic development, the Saudi government plans to invest in construction of large-scale projects such as the Red Sea projects, Qiddiya Entertainment City projects, Amala tourism projects, and so on through PIF. The Red Sea project is a luxury tourism development project located in Tabuk province of Saudi, which will create a high-end tourism destination offering unparalleled marine and very beautiful environmental attractions. The project calls for the development of a wide range of permanent utility assets based on the missions and objectives, including all facilities needed to implement the supply. For example, includes desalination plants, power generation facilities, and demonstration cut and distribution works for water, electricity, and natural gas. Sustainability and efficiency are the basic targets of the project, which aim to leverage renewable energy sources and implement advanced technologies to ensure environmental sustainability and operational efficiency. This project was designed to support the growing population and economic activities in the Red Sea regions, driving economic growth and improving quality of life. In 2019, our company was selected as the EPC contract for the project. Let me introduce the Red Sea project. This project is the first large-scale project in Saudi under Saudi Vision 2030. According to the Saudi Vision 2030 plan, in order to reduce the country's dependence on oil economy and diversify its economic development, the Saudi government plans to invest in construction of large-scale projects such as Red Sea Tourism Project, Qiddiya Entertainment City Project, Amala Tourism Project, and so on through PRF. This project is a luxury tourism development project located in Tabuk province of Saudi, which will create a high-end tourism destination offering unparalleled marine and very beautiful environmental attractions. The project calls for the development of a wide range of permanent utility assets based on the mission and objectives, including all facilities needed to implement the supply. For example, including desalination plants, power generation facilities, and distribution networks for water, electricity, and natural gas. Sustainability and efficiency are the basic targets of this project, which aim to leverage renewable energy sources and implement advanced technologies to ensure environmental sustainability and operational efficiency. This project was designed to support the growth population and economic activities in the Red Sea region, driving economic growth and improving quality of life. In 2019, our company was selected as the EPC contractor for the project. This new city project was divided into lots of packages, and our scope covers all power generation, transmission, RO, or pipeline, cooling generation, waste treatment plant, and so on. The contract value is about $1.5 billion. Because the ETAP TDMI system will provide the top control, monitor, and management of the project, it's very important for me to introduce the scope. This is the overall layout of this project. The area of the project covers about 28,000 square kilometers of lands, islands, beaches, deserts, mountains, and volcanic areas. The coastline is about 160 kilometers. Plants such as PV, BESS, ICE, substations, RO, DCP, STP, sewage treatment, and so on are located in different locations and use plenty of cables or pipe networks to be connected. These 110 kV substations are the heart of the power network system: SF1, SF2, SS1, SSA, and SS7-10. The high voltage underground cable was used to link them. Under these 110 kV substations, there are about 90 33 kV small substations in this project. They are called CSU. These three small microgrids, SDU, DRO, Shibaya, are not connected with the main grid. Each one has its own independent power generation, transmission, water system, water treatment system, and so on. For the power generation, it includes three parts: PV, 406 MW, the BESS, 1.3 GWh, and the capacity of ICE is about 109 MW. All of them are clean energies. Even the ICE use B100 fuel, not a fossil fuel. There are 4 key points of this project. Number 1, the ground size. As reduced before, this is a city-level scale project to build a fully functioning city in the desert with nothing to beginning. 2, the technology challenge is very complex and difficult. Because the power systems are totally cut with the national power grid, which brings very difficulty to control and maintain the stability of the power system because the microgrid is very weak. 3. Lots of new technologies are used in this project. It's very clear, in the future energy landscape, the proportion of new energy power generation will continue to increase. So this project has a strong exemplary role to play. Now, let's move to the second part, the introduction of ETAP's TDMS system in REDC project. This slide shows the master architecture of the control system in this project. From the top to the bottom, there are 3 levels. TDMS is in the top level. All the necessary data and commands will from or to TDMS system through the second level control system. We call it DCMS. Then the loop will connect with the third level EMS to control and monitor of each power generation unit. For example, one ICE or BESS, or even a PV inverter in one plant. This slide answers one question. Why the power system needs TDMS, or what's the function of TDMS in the system? In summary, there are about 4 key points. 1. We use TDMS to manage and supervise the power distribution system. 2. Data acquisition and management. 3. DER control of microgrid. 4. To provide data interface for the variety of applications. Now let's move to some important applications in this system. Number 1, AGC, automatic generation control. 2, economic optimum dispatch. 3, the load shading. And 4, advanced distribution management system. For scope of work, I already introduced in the previous slide. For the scope of work, I already introduced in the previous slide. The TDMS will cover the control and management of the below system. Number 1 is the main grid, and number 2 is the 3 small microgrids. In a classic microgrid system, some important controllers are needed. For example, number 1, the generation management and EMS. Number 2, meter data management and settlement system. The next one is for the microgrid management. And the EMGC is another important controller in the classic microgrid. TDMS is the very important ones. And the last one is the demand side management system. The objectives of TDMS is to provide a shared network model and a common user experience for all rules that are required to monitor, control, and optimize the secure operation of the electrical distribution network to maximize reliability and allow users to get benefit from the cost optimization. For example, TDMS can dramatically reduce the operation team, which can save huge costs in operation. In this project, ETAP TDMS system shows a very good ability and performance in the microgrid control system. The detailed TDMS functions are shown here. Number 1 is the UI system. ETAP provides the simple, beautiful, and functional HMI in this project. Number 2 is the operator models. Number 3 is the distribution management. The fourth function is the network management system. And the outage management is another one important function. The integration and interface is the sixth function of this system. Now, let me introduce some findings or optimizations in the control of power system. The first case is voltage and frequency regulation of the microgrid. In this project, we use the concept of three-level frequency control. We all know there's direct proportional relationship between P, active power, and F, frequency, or Q, reactive power, and U, voltage. So, when the system detects the change of frequency value and the voltage value of the interface point, the corresponding command to change the P and Q will send to the generation unit. The three-level philosophy. Number one is the primary frequency control. Primary frequency control means the power generation system independent regulation. It has a very fast reaction, but it cannot monitor all the values in the power system. So the adjust value will not very accuracy and not the final value. Then system comes to the second frequency control. This is centralized adjust. TDMS system will calculate and send the target frequency value to the generation and monitor the feedback value. Of course, this will take a longer time. After that, TDMS will continue monitor and compare the frequency value with the standard one. If there are still gaps, the third level frequency control command will send it to the generation for the final adjust. By this operation philosophy, TDMS can maintain the power system work stable. The second case is the optimization of ABTS in this project. ABTS means automatic bus transfer scheme, which is the practice of transferring a load bus to an alternate source when the normal power supply fails or is tripped, thus entering continuity of power supply. This drawing shows how the ABTS works in this project. In the original design, the command of the just POQ or base is from TDMS. However, there's a conjectural defect here. Due to the communication mode adopted by TDMS and the multi-level relationship between them, the process will exceed 100 or even 200 milliseconds. This causes the switch speed to be very slow, which affects the stability and continuity of the power supply. So during the execution stage, we optimized the architecture of the ABTS, and the key point is to reduce the loop length of the communication. By doing so, can reduce the time duration. The next slide will demonstrate the new concept. The SLD in the right side shows a typical structure in this project. This is the normal status. Suppose there's a fault at the incoming side of bus 1, for example. When fault here, it will cause the trip of switchgear 1. Now, the left side will come to the island mode, which means it was totally isolated with the power grid. In this case, the electrical parameters of the island side may differ with the power grid. So the PQ adjust and control to meet the same frequency and voltage are monitored before the synchronization. After that, the DCMS will start the auto mode. DCMS will send adjust command of base A to EMS, then to PCS by the following calculation. For example, if frequency 01 is smaller than frequency 2, system will send increased power to PCS until the difference of them reaching the setting value. If the frequency 1 larger than frequency 2, system will send reduced power to PCS. If the voltage 1 smaller than voltage 2, system will send increased Q to PCS. If voltage 1 larger than voltage 2, system will send reduced Q to PCS until the difference of them reach the setting value. If within the setting time, for example 3 minutes, the bulb adjustment failure, system will return to manual mode. The 6 steps DCMS will send sync OK to EBTS. If all other conditions OK, EBTS will send the close command to bus coupler breaker. Then the 7th step, the bus coupler CB S02 will close by the synchronization relay. After this S02 closed, the totally EBTS process complete. So by this change or by this optimization, we can achieve the faster response of the EBTS. Dear Madam and gentlemen, due to the time limitation, today my presentation will come to the end. Thank you for the watching, and I wish the ETAP Spark 2024 will be a success. Thank you very much.